test if it's...
Yeah, seems to be working. Yeah.
Let's wait a couple minutes. You still don't have one.
That's fine. I mean, they know what is going on.
No, you don't know what they need.
So can I move with this microphone all the way there and there?
Yes.
Because the other one, there was some...
No, this fine.
One is fine.
You need a pointer also? Additional?
Yeah, I thought that this has a point.
Yeah. It's not a very good pointer.
I have just a few slides.
Okay.
I mean, I want to show some motivations.
What should we do?
They saw Matthias' lectures. Yes.
Look who's here. How are you?
Yeah.
Okay, good morning, everyone. We're starting the second week of the school. I hope you had some rest during the weekend, not too many caipirinhas. I'm super excited about the second week. I think you guys are very lucky, very privileged to have 3 excellent lecturers for the second week. So the first lecture of the day is Professor Marko Simonović. So Marko is an expert in the field of relation theory. He did his PhD at CISA, then spent 5 years at the 4 years at the Institute of Advanced Studies in Princeton. But I got his T-shirt, his sweatshirt. And now he's at CERN, in the theory group at CERN. He's a staff at the theory group of CERN. And so he's going to talk about perturbation, the second week of the large-scale structure course.
Thank you. Thanks a lot, Rogerio, for a kind introduction. I'm very happy to be here. This is not my first time in Sao Paulo, and it is great to be back.
You should get the microphone a little bit up, if you don't mind.
Yeah. Better? Is it better? Yeah. Okay. So, right. So the idea for this course is to be something like advanced topics in large-scale structure. Okay. This is a school on observational cosmology. So let me first ask, how many of you have seen or used or dealt with perturbation theory in the past? Anyone? Yeah. So quite a bit of people. Yes, it is a standard tool that we use when we try to describe clustering of matter on large scales. And no matter what you do, one way or another, you will have to deal with some sort of perturbation theory, both linear and nonlinear, if you do cosmology. This is something which is unavoidable. And these lectures are going to be more like methodological lectures, where I'm going to try to explain how this perturbation theory works. You saw last week the solutions to the linear theory, and we are going to start from there this week. And basically, I'm going to show you how to go beyond linear theory, because we know that in the late universe on large scales, the clustering basically eventually is a nonlinear, and we need some tools to describe it, and I'm going to explain what are these tools. But so before I will try to do most of the things on the blackboard, such that I go slow and you have time to see the details and maybe ask questions. Feel free to interrupt me at any moment in time. But before I do that, let me say a few words about some motivations. Why do we need to do these things? And I'm going to show you a few interesting results at the very beginning. And then we're going to start basically the course, okay? So you probably have seen all these things, like not only last week, and you're going to see some of these this week, but also in general. In cosmology, we have a very nice model, lambda CDM model. This is a standard model of cosmology. It fits all observations very well. But we know that there are some interesting questions that we want to find answers to. And for that, we need to measure things more precisely, more carefully. And there are many questions that are interesting. I list here some of them, and we can discuss about that during this week. And I'm sure that you're aware of all these issues. Things like measuring neutrino masses, understanding if there are some extra relativity degrees of freedom in the early universe, exploring possibilities to measure primordial non-Gaussianities, and so on and so forth. So all these things are very interesting, and we cannot do what we could do, we did with the CMB, and the next big frontier is to try to use the information from large-scale structure to extract additional constraints on some of these parameters, and maybe possibly find some new physics or some surprises. We never know. Now, there are many questions which are pretty big questions, but unfortunately, they leave very tiny imprints in the late universe. For instance, if you have some small amount of non-Gaussianity, which is still allowed, for example, by constraints from the CMB, then this is going to lead to 0.1% corrections in the density field in the late universe. And so therefore, you have to work very hard to make sure that your predictions, theoretical predictions, that your systematic error bars from the surveys and so on are kept under control to be able to measure such a tiny effect. Okay? So statistical error bars are small enough. In other words, if you just do the mode counting, if you just count how many Fourier modes there is in the observable volume of the universe, it is more than enough to reach this kind of statistical power. So the error bars, if you have large volumes, are going to be very tiny. But the real question is, like, can we match these error bars in our theoretical calculation? And this is what I'm going to talk about. And there is the whole aspect of, can we match these error bars in terms of all systematic error bars that come from processing the data? And this is another set of questions I'm not going to talk about, but they're also very important. All right, so now let me just very briefly remind you about what you have already seen last week, hopefully. So what is shown here is the linear matter power spectrum. So there are a few characteristic features in this power spectrum. Let me very briefly remind you what they are. So on large scales, the power spectrum, the linear power spectrum is proportional to k. So this is because the initial power spectrum is scale invariant. So you have seen from inflationary lectures that the curvature fluctuations, which are basically on large scales proportional to gravitational potential fluctuations, they have the scale invariant power spectrum, meaning that the power spectrum goes like 1 over k cubed. Do you remember that? So the linear power spectrum or primordial power spectrum for curvature fluctuations or gravitational potential looks like 1 over k cubed. And therefore, when you use Poisson equation to go to delta, you get 2 times the square of k. So 2 times, you have to multiply 2k squared, so you get k to the 4. And that's why 1 over k cubed turns into something proportional to k. So on large scales, you have scale invariant power spectrum. But then, on small scales, or high wave numbers, there are all these features. So first of all, there is this point here where the linear power, where the scale invariant power spectrum turns and goes down. And this happens for the Fourier modes that enter. So basically, this scale is decided by the equality time. So if the Fourier modes are enter the horizon before radiation matter equality, then the power spectrum is suppressed. Otherwise, the longer modes always have the same power spectrum as initial conditions. So you saw some of these things in the CMB lectures, I'm sure about that. And then there is another interesting feature, which are these wiggles in the power spectrum. And these are famous, well-known BAO wiggles. And you also saw that thing last week. So all this information, so all these features in the power spectrum, so the shape of the power spectrum depends on cosmological parameters. It depends on that, what was the recombination physics, like what was the expansion history of the universe, how much matter you have, how much dark matter, baryons, things like that, okay? So, so if you look at this, power spectrum, so if I ask you, what power spectrum represents physically? Do you know the answer? Like, what is the meaning of this curve? How should I, is there some simple physical interpretation? So what do I know about fluctuations? For instance, at which scales the fluctuations are the largest, if I show you this power spectrum? What will you say? You remember that the power spectrum is some expectation value of two density fluctuations. So where would be the largest fluctuations if you look at this power spectrum? No answer. I was hoping that, well, not hoping, but you may think naively that maybe at these scales the fluctuations are the largest ones, because here is where the power spectrum peaks. But this is not what is the relevant quantity. This is like all in Fourier space. So you should, if you want, for example, to calculate what is the typical size of the fluctuations of the density field in real space, what we really care about, you have to calculate the variance of the power spectrum. You have to basically do the Fourier. You have to integrate over all Fourier modes smaller than the typical size of the region that you're looking at, and then you're going to find what is your answer. And this variance is some integral in d3q, d3k times p linear of k. And so approximately, it is almost the same as just multiplying the power spectrum with k cubed to make it dimensionless. And this dimensionless number, because the power spectrum has units, because it is in Fourier space, so this dimensionless number is the reduced power spectrum, or closely related to the variance of the density field. And because you're multiplying by k cubed, the previous curve, then actually, if you ask yourself, if you look at these scales here, you see that the density fluctuations are typically very small. So if you basically look at the regions which have size which corresponds to these wave numbers, which are pretty large regions in space, and you smooth the density field on these scales, you have a very small density fluctuations. So as you go to larger and larger scales, the density fluctuations are getting smaller and smaller. But if you go to small scales, at some point, the density fluctuations become of order 1. And this happens, roughly speaking, around k of 0.2, 0.3 at redshift 0 for lambda CDM power spectrum. So this is a very rough estimate of a scale where your density fluctuations, typical density fluctuations, if you throw like a spheres of roughly 10 megaparsecs, you're going to find that typical density fluctuations of order 1, okay? So this is what we mean that when we say that our universe on large scales has small fluctuations, on small scale has large fluctuations. We have in mind this curve. And of course, when fluctuations are large, intuitively it is clear, because gravity then becomes very strong, that it is very difficult to describe this evolution. So this course is going to be about attempts to describe evolution on large scales, to see what happens here. So this is, again, a reminder from the previous week. And now let me show you a few things. Let me make a few promises that what would you be able to do if you follow this course, okay? If you try to use the formula that I'm going to show you, like what kind of results you can expect to get. So what is shown here, for instance, and the major question, of course, is going to be how do we deal with this nonlinear evolution? Let me show you a few results. For instance, if I calculate the nonlinear evolution on large scales in perturbation theory, as I'm going to explain to you, you can, for instance, calculate the correlation function in real space. And so what is shown here is the measurements from some very large volume simulations, so with very tiny error bars. Then there is the linear theory, which is the blue curve. And you see that the linear theory doesn't fit the data. This is not a surprise. This is because there is some nonlinear evolution induced by gravity, and we expect that the linear theory doesn't work. But you can see that, for example, if you do something like one loop calculation perturbation theory, I'm going to talk about that today and tomorrow, then things become much better. So now you have a curve which goes very nicely through all data points, all the way to scales which are roughly 20 megaparsec or so, okay? Which in the power spectrum corresponds roughly to k of 0.2 or 0.3. So we are indeed able to calculate things, okay? So here, the only thing that comes from the simulation here are the data points, but the curves are theoretical calculation. And I would like to show you how is this possible. How do we get there? What kind of reasoning is behind this calculation? So next.
So I can ask a question about this.
Yes.
So at large scales, you would expect linear theory to be okay, you know, but still find some differences at
Yeah.
large scale.
Yes, and I'm going to explain, I think on Wednesday, I will talk in great detail about that, like why there is this broadening of the BO peak. Where does it come from?
About even 140, 120, there's no.
Oh, here?
Yeah.
Oh, yes, this is all about the broadening of the BO peak. Yeah.
Okay, it's all about the broadening.
Yes, I think that you see that there is a sharp like feature in the initial conditions, and then you smear it here, and it leaks a bit here, and so it's all about the broadening. Yeah. And I'm going to discuss this in great detail. This is just some motivation to motivate you to say, look, we can do like precision cosmology for real. I mean, it's not some approximate thing. Then, let me show you an example. This is not published. It's something that we're preparing to put online. There was a perturbation theory challenge designed by Takahiro Nishimichi and Masahiro Takada. So they gave us the output of very large volume, roughly 500 gigaparsecs cube, much bigger than Euclid or DESI or even the observable universe at this redshift. So they gave us a very large volume outputs where they measured the observables. So these are simulations which have galaxies and satellites. They're as complicated as your data are going to be. And the challenge was that to use our analytic models to basically recover cosmology from that, okay? It is not lambda CDM cosmology. It is not Planck cosmology. It is lambda CDM with different parameters. And the challenge was to get it right. And let me just point out that the error bars, this is the monopole and quadrupole. I will explain also what these quantities are later on during the week. But the error bars are so tiny that you cannot see them in these plots. So if you look at the residual plots, this is the 1% on this scale. And the error bars are much smaller than this, for example, for the monopole. So if you make any kind of error in your theoretical modeling, you will get a wrong answer. And luckily, we were successful. We were able to get the right cosmology. And all cosmological parameters are measured better than 1%. So this volume is big enough that without any priors, only from large-scale structures, even though you're looking at the galaxies in redshift space, you can reliably recover cosmology to better than 1%. Okay? And this is really an impressive precision. So people usually talk about 1% as something which is a standard for having a good precision, but here it is even better than that. And all that you can do with some simple reasoning and a few simple formulas. So it's very interesting to learn what is behind these formulas. And it is not only about like some simulation or something like that. You can apply the same pipeline to the real data. And this is, again, some preliminary results that hopefully will be out soon. The plan was to do it this week, but now there is another. You're postponing it a bit longer. But some preliminary results from the BOSS analysis of the galaxy clustering using the same pipeline and measuring the same power spectra. And these are the results, for instance. And you can focus on these blue curves, which use 0 prior from the CMB. So there's absolutely no information from the CMB whatsoever in these contours. So no sound horizon, no omega matter, no omega barrier, nothing. So the BOSS data are powerful enough alone to basically measure Hubble or omega matter as good as Planck. This is not what is usually advertised, or it's not what you usually find in the BOSS papers, because somehow, unfortunately, they always either put Planck priors or do analysis in a different way. But this is the kind of error bars that we get even from the current surveys. So from the data which already exist, it is already competitive with Planck, okay? And in the future, things are going to get much better. So for instance, this is one example from a very recent paper which uses the same pipeline to make a very sophisticated forecast for Euclid or DESI-like survey. And the blue contours here are Planck, is a Planck 2008 likelihood, and then you should compare that with the green contours, which comes from this future like DESI or Euclid-like survey, and you can see that there is a huge improvement in all cosmological parameters if you combine the two. So all these things are going to happen, and now the question is like how are we going to analyze this data? I showed you some results, and I think that these theoretical models are going to be still the major tool that we're going to use to interpret the data and extract cosmology, at least from the galaxy clustering. So the purpose of these lectures is to guide you through these calculations which are behind these theoretical curves, and to show how to make predictions for the galaxy clustering from the first principles without using any like simulation or any approximations, nothing whatsoever. So you can start from the Bunch-Davis vacuum in inflation. You can evolve the fluctuations all the way to the CMB, go through the CMB, go to the late universe, do only reasoning and formulas and calculation, and predict how the galaxy clustering looks like with very high precision. I think this is an impressive story. It is really amazing that we are able to do all that despite all the complications which enter the structure formation, but it is true. Now the focus will be mainly on applications. I really want to skip too many derivations. I'll fill some things for you to do, but I want to point out some key things and then also show, like, basically always talk about things that are related to observations, such as, for example, the nonlinear power spectrum. This is going to be the main thing that we're going to talk about. So the plan is that today we discuss a bit about, so the first 3 days are going to be about dark matter only. I'm going to talk about today about what are the correct equations of motion to solve and what is this EFT approach to perturbation theory. Then we're going to discuss maybe tomorrow the dark matter one-loop power spectrum, which is basically an example of this kind of calculation that is needed for these comparisons to the data in some detail. Then on Wednesday, I'm going to talk about this IRS summation and the physics of the BO peak, explaining, again, in some detail how this broadening happens and how to calculate it, okay, without free parameters. And then, finally on Thursday, I will say a few words about bias tracers, redshift space, power spectrum multiples, and so on. So how do you put on top of dark matter, how do you put baryons, how do you put dark matter halos, galaxies, things like that. And if you have time, because I'm not sure how long it's going to take to do all this, then on Friday we can discuss a bit about some more advanced things, okay, which are related to the recent methods which go beyond endpoint functions. Okay, does it sound good? Yeah. So this is also, I'm going to leave these slides, you will have access to this. So, but there are a few nice lecture notes which cover some of the things that I'm going to talk about by Leonardo Senatore, Mehrdad Mirbabai, who was teaching inflation, and Tobias Baldauf. You can find them in these links. Also, Matias Alderiaga gave a very nice set of lectures in this very school 2 years ago, and I encourage you to go and see these videos. I mean, these lectures are really, really, really good. There are a few other, from time to time, I'm going to also point out to some papers that you may want to look at, okay? But these are the lecture notes which cover more or less what I'm going to talk about. So the plan for today is to really do the nonlinear equations of motion, explain a bit what is the CFT, find some perturbative solutions. And if you want to read about these things, there are 2 papers, I think. The original paper from 2010 that started, and where for the first time it was realized that something like EFT approach is needed for large-scale structure, and then the calculation of one-loop power spectrum, which came out a few years afterwards. So there is a lot of literature which came after that, but if you want to go back and read the original, this one in particular is very pedagogical. It's a very long paper, but it explains things in great detail, and you may want to take a look into these 2 references in case you're interested to know more about it. All right, so okay, so this is where we want to end. But maybe I can just close the computer. Oh, I can leave it. It's fine. So that is some very brief general introduction to give some context and to tell you what I'm going to talk about, to show some promises that if you follow the lectures, you will be able to make these amazing predictions. But let me ask now, do you have any questions about this before I move on to the Blackboard? No? Everything is clear? Yes?
Do you mind just speaking a little louder?
Louder? Bring the microphone up. Sorry, yes, that's the... I'm not sure if it is better or worse because it's better. Is it a bit better? Okay, but remind me because I think that I will be tempted to like become quieter again. So please shout, say like we don't hear you. Please interrupt whenever you want. Okay, so if there are no other questions, then let us start with we're going to the Blackboard, and so now let's see how this goes. I mean, I was impressed by these large chalks and this large Blackboard, so I'm like very happy to like have a chance to use it. So let me begin. So of course, what we're trying to do is to understand some system. And if you want to do it in an analytic way, the first thing that you always ask is like, what is the dynamics? What are the equations of motion that I'm trying to solve? Okay. So if you look, let us also start with considering the dark matter universe only. So for the first couple of days, we're going to do dark matter only, okay? So later we're going to discuss how do we deal with baryons, galaxies, and things like that. But let me just imagine that somebody comes and gives you the dark matter universe only. And this is what happens in n-body simulations, right? You set up an n-body simulation. You say, well, I'm going to put some initial conditions. I'm going to use the linear power spectrum to generate, I don't know, Z-W displacements. I start my simulation, and then it evolves. Dark matter particles interact, form halos, clusters, filaments, all this cosmic web, okay? So let us try to understand how can we describe this system. Let's say that our universe lives in the dark matter simulation only. And can we do something about it? Now, obviously, the full equations of motion for this problem are basically equations of motion for each particle which interacts with everybody else, okay? But of course, this is impossible to solve analytically, right? Or equivalently, you may say that you have, because dark matter particles are collisionless, you have the full Boltzmann equation that you have to solve, and you have to know the distribution function in phase space, which tells you for each position in space how many particles there are there, and what are their velocities, and so on and so forth. So it's like a very complicated system. And this is hopeless to do in full generality, okay? So we cannot solve the full system. But there is some sense in which this system looks more under control if we focus only on large scales, okay? And if you focus only on large scales, then the dark matter behaves more like a fluid, and we can use more tractable and simpler equations to solve, which are fluid equations. So let me first write down these equations that you probably have seen last week and in the past. I'm sure that you saw this before. So there are a few things that we usually write down. So there is delta prime plus divergence of 1 plus delta v. Okay, this is equal to 0. Can you see, by the way, this is not too small, yeah? And then, so this is called the continuity equation. And then we have Euler equation, which is time derivative of the ith component of the velocity plus h vi plus dj v, sorry, vj vi equals minus gradient phi, and then minus 1 over rho dj of some tau ij. This is the Euler equation. And finally, we have Laplacian phi, or let me do this, equals 3/2 omega matter h squared delta. So have you seen these equations before? Yes. Is there someone that has never seen these equations? Probably not. I mean, these are standard equations that people write down when they talk about cosmological fluctuations and perturbation theory. Now, the thing is that I want to say a few words about these equations, to spend some time discussing what do these equations actually mean and how to make sense of them. Because the way that they're written now, I'm not going to derive them because usual derivation starts from the full Boltzmann equation. You write down the full distribution function. You find the moments. You plug the moments back to the Boltzmann equation. You get these equations of motion. So everything seems fine. But intuitively and physically, these equations, in some sense that I'm going to discuss now, do not make much sense. Okay? It is not obvious. Yes?
Oh, sorry, just for notation. So you're using conformal
right.
time.
Let me specify. Yes, the prime is derivative with respect to tau. Tau is conformal time. And Hubble is also conformal Hubble.
I'm not sure I'll introduce the last term in the algorithm.
This one?
Yeah.
Why? Rho? In what sense? So this rho is, well, I guess it's just some kind of a definition. This is the rho bar, if you want. No, sorry, this is the full rho. This is the total density. Yes. Okay, I'm going to mention that what this part is. So this is one thing that I'm going to discuss in great detail. So probably what you okay. So these equations are of course they're in conformal time. Thank you. So then delta is the standard density contrast, which is defined like well, you know what it is. I mean, I don't want to repeat. And v is like peculiar velocities, velocity perturbations, all in moving coordinates because all bulk flows are already taken into account. Sorry, not bulk flows, but the Hubble expansion. So now, what I wanted to say is that, and finally, this last equation, of course, is a Poisson equation, which tells you how the gravitational potential is, or fluctuations of the gravitational potential are related to the fluctuations in density. So now these equations are equations of motion that you can derive from the Boltzmann equation or Vlasov equation. But the thing is that, and usually you say, well, look, they look like a fluid equations. But the problem is that it is not clear what does this really mean. Okay? Yes?
The Nabla in the equation is just a partial.
Yes, sorry. I think that maybe I'm going to interchangeably use both of them.
No, just to check because.
Yes. Yes. So nabla or partial probably is the same for these purposes. I might use one or the other. I don't know. But thank you. Yes. So these are the same things. So why there is a problem in saying that, oh, these are the equations of motion that I want to solve. They look like fluid equations, so I have a dark matter fluid on large scales. The reason why it is not so clear what to do is because there is this term here. Okay, this term here is the stress tensor, which is yet another. It is related to yet another moment in the Boltzmann hierarchy, and it has its own equation of motion. In principle, Boltzmann equation is always rewritten formally as an infinite hierarchy of different moments, like sourcing different equations of motion. So the question is, like, how do we know that we can truncate this long Boltzmann hierarchy and just say that these are the fluid equations of motion that we're trying to solve? Okay, that is a big problem. So more intuitively, what is happening is that dark matter particles are collisionless, which means that if you have like two bunches of dark matter particles, when they cross each other, they just go through each other. And so you cannot describe this process as a simple fluid, because fluid requires to have a single stream. Okay? But this shell crossing and this complicated dark matter behavior and this free streaming of dark matter particles causes the problem. And in principle, for the collisionless particles, if you have a bunch of particles which can just go through each other without interacting, the fluid description in general is not a good description. Okay? So then the big question is, why do we declare I mean, just think about this. Imagine that I give you a box where there's two sets of particles whose velocities are just pointing in the opposite direction. They will just go and bounce at the walls. If they don't interact, they will never become a fluid, okay? So fluid requires to have some mean-free path, okay? If you don't have a mean-free path, you cannot talk about fluid. And if you have a mean-free path, then on scales much longer than the mean-free path of the particles, you have a fluid description. But on scales much shorter, you don't have a fluid description. You have random particles flying in all possible directions. And so because dark matter is a collisionless fluid, how do we know that, or is a collisionless dark matter actually, how do we know that it becomes a fluid? How do we know that we have right to think of it as having a single fluid element which just has a single well-defined velocity and it has some flow? So that is a big question, which is usually not discussed when these equations are shown, okay? People usually just neglect these questions and say, okay, let's move on to solve something. But there is this big conceptual question. And this question leads to some very important consequences. This is why I'm spending so much time. So is it clear what is the problem? If you don't have a mean-free path, if your particles never talk to each other, and they're allowed to travel through each other without ever interacting, you cannot use fluid description. And one example where this happens in cosmology are neutrinos. So if you try to understand how neutrinos evolve in the early universe, you have to solve the full Boltzmann hierarchy. You cannot approximate them as fluids because they're very fast, they free stream, and there is no fluid description for neutrinos. So what allows us to use fluid description for dark matter? Do you have any ideas? Why we are allowed to say, at the end of the day, we will be allowed, but how come? What gives us this thing that we can say, no, there is a reason that dark matter is fluid? What is this reason? Very good. You may say that maybe somehow at the beginning they were interacting, became like a fluid. But we know that if that is true, they would interact too much. So we would have a different structural formation. CMB acoustic peaks would be different and so on. It requires too much interaction. So we know very well from observations that dark matter is pretty much collisionless. Particles do not really talk to each other very much. So there are two reasons why we are allowed to approximate dark matter as a fluid, okay? So the first reason is that there is some scale which is roughly 10 megaparsecs, which is the scale that dark matter moves. So dark matter particle moves in the age of the universe. So it is not true. I mean, it is true in some sense that, the dark matter system is collisionless, but the particles cannot move arbitrarily far away because they're very slow. If you calculate the typical motion that dark matter particles do, it is not more than 10 megaparsecs, a few megaparsecs, okay? So therefore, there is some effective mean-free path. The dark matter particles remain localized. So if you have, like, for example, a bunch of dark matter particles in the initial conditions, in your simulations, they will move. Maybe there is an overdensity here. So for example, they all move like towards each other, or maybe they move here in this other direction. But these typical displacements are at most of order 10 megaparsecs. So it's not that the dark matter particles travel across the universe, and then you don't have a fluid description. So what this means is that if you look on scales much larger than these 10 megaparsecs, you should see still coherent flows, because any chaotic motion or any like free streaming issues are only localized on small scales. So the finite age of the universe plays the role in providing, in a sense, a mean-free path for dark matter particles. And the typical scales are those scales. And there is a second reason, which is formation of dark matter halos. So it is not true that dark matter particles are just some like bunch of particles fly around that they can free stream and so on. They don't talk to each other, but they still interact gravitationally. So this is a system of equations where there is gravity, and it plays a very important role, which means that if you have a big clump of dark matter particles, they will not talk to each other, but they produce gravitational field, and they will start collapse, okay? And more matter will fall in and form a bigger halo and so on. So in some sense, they're sticky. They stick to each other, okay? So these two things are important in order to say that there is some sense intuitively why do we expect dark matter to be like a proper fluid. Because on scales larger than the typical size of the halos, or these 10 megaparsecs that, or a few megaparsecs, which more or less the same scale, where some complicated things are happening. On larger scales, things must be more regular. And so there is a sense in which dark matter fluid is a proper fluid, okay? Yes?
I didn't quite understand the first argument. So when you mentioned that after 10 megaparsec, it moves in the age of the universe, does that mean that it just follows the Hubble flow without any particular direction?
No. These 10 megaparsecs are peculiar velocities. They're induced by, for example, local gravitational field. These are on top of the Hubble flow. So there is a Hubble flow, and on top of that, I think there are displacements because there is a big overdensity, and dark matter particles are pulled towards this big overdensity. They move by, roughly speaking, moving coordinates by roughly 10 megaparsecs, yes. To get this estimate, you can ask yourself, what is the typical dark matter particle velocity in like some cluster or in some like a halo? And you will find that actually it is, roughly speaking, few hundred kilometers per second. And if you multiply this with the age of the universe, you're roughly going to find a number which is roughly 10 megaparsecs. It's a very rough estimate, but what it means is that dark matter particles cannot go to 100 megaparsecs from where it originated because it doesn't have any velocity initially. Okay. So very good. So now, this motivates us to try to find the equations of motion which are such that, so remember, still here, there is this stress tensor which comes out from this Boltzmann hierarchy. And this stress tensor tells you about all these velocity dispersion, about these complications which are happening on small scales. And there are other moments that I didn't write down which also are equally relevant to these small scales. So what we want to do is to stay on large scales. So never discuss what is happening on small scales where we don't know what to do, but rather than discussing small scales, stay on large scales, okay? And then what we want to do with these equations is somehow to write down equations of motion for only long wavelength component of the density field. We don't want the full density field or full velocity field, which also involves small scales. We want to focus on the dynamics of long wavelength modes, where we're staying away from the trouble, okay? And I'm going to denote this with delta long and V long. So these are long wavelength fluctuations for which we believe that some decent fluid description exists, and we want to find what are the equations of motion for those two. Now, what do we do then? Okay, so the usual approach in a lot of perturbation theory literature is to say, if I'm interested in the long wavelength fluctuations only, then I should not be worried about what happens on small scales. So I can safely neglect this stress tensor, okay, because this stress tensor has to do with the velocity dispersion on small scales. On large scales, it goes to 0. So I can neglect this thing. And then what you get is a system of equations which look like ideal fluid coupled to gravity, okay? So for ideal fluid, there is no stress tensor whatsoever, and you have this set of equations plus this gravitational potential which is sourced by the density fluctuations through the Poisson equation, okay? And so this set of equations where you neglect stress tensor is what is usually called standard perturbation theory, or SPT. Have you heard about it? Yeah, probably you did, because this is something that people have been doing for a very long time. It is the standard approach in cosmology, okay? But it does this assumption that you can simply neglect this stress tensor. When you talk about long wavelength fluctuations and want to describe the dynamics of long wavelength fields, just ignore this. However, this is not possible. What I want to argue now, so the next thing that I want to argue is that this is not consistent. You cannot do that. There is no way to do it. There is no sense in which you can just ignore this stress tensor. You have to do something a bit more sophisticated, okay? And to understand what this slightly a bit more sophisticated thing is that what you can try to do is to start with this full set of equations and try to smooth on some scale R, okay? So what do I mean by that is that any field, if you have some field x, which is a velocity of delta or anything, so any field smoothed on some scale R at some point x is just going to be simply given by the integral. This is a very simple thing. So it's just the integral of d3x prime. Then you have a window function, x minus x prime, and then times x divided x prime, okay? So the smoothed density, well, for example, the smoothed density field will be the full density field where you apply some smoothing filter. It's a very simple thing. For simplicity and for concreteness, we can imagine that this filter here is given by a Gaussian, so it's proportional to something like e to the minus x prime squared divided by 2 times r squared. For instance, you have some nice, simple Gaussian filter, and you just multiply your density field with your Gaussian filter, integrate over all possible x primes. And because Gaussian decays at large distances, this is the same as effectively looking at the region centered around x with a typical size r, and in some sense averaging the density field. So this is what is the smooth density field, all right? And then there is a long procedure, which is a bit tedious, but it is instructive for you to do, and I'm not going to do it, is to apply this smoothing procedure to these equations of motion. Okay? So if you do that, you're going to discover that there is no sense in which you can neglect stress tensor, because even if you start with equations of motion which do not have this piece, it is going to be naturally generated by the smoothing procedure. So if you want to talk about long wavelength fields only, unavoidably, there will be always some short scales that are going to produce the long wavelength fluctuations, and they're going to produce some effective stress tensor here that you cannot get rid of, okay? And just as an example, one of the exercises that you can do, for example, you can try to calculate this. I mean, the solution is in one of the references that I gave you, so you can just take a look and follow the calculation in one of the papers that I mentioned. So what happens if you try to take the product of two functions, f and g, and then smooth them on the scale r, okay? So what will be your naive answer? Let's say that when I talk about long modes here, let's say that anything which is the fluctuations which have the wavelength longer than the typical size of the region are long wavelength fluctuations. Those that are shorter than these are short wavelength fluctuations. So the typical answer would be, well, this must be something like long wavelength part of f times long wavelength part of g, right? This is what you would naively say. Okay, if I just take two fields, I make a product and I smooth, roughly speaking, is the same as multiplying two smoothed fields. But not exactly. You see, this operation of multiplication and smoothing is not commutative. And in fact, the answer is a bit more complicated. So first of all, there will be always some part which is f short, g short, some random short fluctuations, smoothed on the scale r. And this simply comes from the fact that when you split these two guys into the long and short modes, there will be a product long and short. But there are also hard derivative corrections. And in fact, there are infinitely many corrections. There is, for example, r squared, okay, with this ambiguity in the notation, let me do partial derivatives this way, DIF long and then DIG long plus dot, dot, dot. There are infinitely many terms in this formula. Okay? It never stops. They're all possible higher derivative terms. And you can try to do this exercise. It's very instructive. So what does it mean? It means that if I have any sort of products of the fields, when I smooth them, I unavoidably generate a lot of terms. And some of these terms depend on the long modes, but some of these terms still contain the smoothed density field for the short modes. And those kind of complicated terms, which are going to appear in this lengthy procedure of smoothing these equations of motion, what is going to generate some effective stress tensor on this side that you can never get rid of. Okay? Well, I think that, so roughly speaking, well, the long mode here is almost is the same as just smoothed a single field. Okay? So this is what we mean by the long mode. It just means that, like, well, if it has a wavelength longer than the smoothing scale, when you apply operation of smoothing, it doesn't change, right? So this is what it is. But for example, if you have some short mode and you smooth it, it will become 0 because this is what it is, right?
This expression for the product, have you assumed something on the window function?
Yes. Well, like you have to make some assumptions. For instance, like in this particular case, I used the Gaussian filter. So for instance, there is a step in this calculation where you have to do this integral, d3x prime, x minus x prime I, x minus x prime j, and then the window function of x minus x prime. And this turns out to be r squared delta ij. So you may think that this is just a definition of the smoothing, because if you have like the product of two typical distances from some point x, and you smooth it with a uniform thing, you're also going to get something which is r squared. Yes, it's the average. So basically, it's really like this window function is an averaging function. So for Gaussian, this really happens to be the case. This is the exact formula. But you can think of it even as a definition of what a smoothing means. But that doesn't matter. You can just use the explicit Gaussian. So there is this step in the derivation. You can take a look in the paper.
So wouldn't you expect when you take this region, smoothing region, to be very large?
Yeah, so if the smoothing region is very large, So the thing is that I think that taking the smoothing region to be very large is a bit complicated, but maybe to explain, maybe the better thing to do is to look what happens with the wavelengths of these long modes as they get longer and longer and keep the smoothing region fixed. So as I do this, imagine now that I'm looking at some very long wavelength fluctuation, which has, and for example, this is a typical size of my smoothing. So I have very long wavelength modes compared to the smoothing, then these derivatives are going to be 1 over the wavelength of the fluctuations, roughly speaking. And you're going to have some parameter, which is r squared over a wavelength square. And this is a very small number. So you see, this is the intuition why this smoothing doesn't matter so much for a very long wavelength fluctuations that are much larger than the size of the smoothing. Probably this is what was your question. So for example, this term, in some sense, can be neglected. It is much smaller than this term. And there is a parameter now, which is the wavelength of the fluctuations compared to the smoothing scale. And this is exactly what we want to achieve here. We want to start with these equations of motion. If you do this smoothing procedure, we're going to end up with equations of motion only for the long fields. And there will be many extra terms, but their relevance is going to be small in this sense. We cannot neglect them because this depends on how much precision do we have and what are the typical scales that we care about. But in principle, we can take them into account. And if you add more and more terms eventually, they're so high power in r squared over the wavelength square that you can simply neglect them. Okay, so this is the major idea. So what happens when we do this exercise? Let me just write down the final solution. So the final solution is that if you want to do the equations of motion, and you can find the details of this derivation in these references, but it doesn't make sense to go through all these steps. The final solution is that delta long prime, so now I'm writing equations of motion for the long wavelength part only, plus, you can rephrase everything in the following way. 1 plus delta long V long equals 0. And the second equation is V long I prime plus H V long I plus V long J, and then dJ V long I equals minus gradient phi, gradient phi long. And then there are two terms here. Well, let me say that. Well, let me write it down. It will be 1 plus delta long times dj of some tau ij tilde, okay? So which basically has only long wavelength components. So now it is not the same thing. So if you do the Boltzmann equation, for instance, you're going to find the velocity dispersion here. There is some formula for this stress tensor. Now, when I smooth these equations of motion, because of these extra pieces, it becomes more complicated. They preserve the same structure, but now there is some new effective stress tensor, which has a new form. And this is why I'm denoting it with a tilde, okay? So what you can see is that equations of motion are pretty much the same, except that we were very pedantic and we were keeping this piece here, okay? So what is this stress tensor? And so from the intuition that you had that we had when we discussed this smoothing, it should be clear that this stress tensor depends on short and long modes, okay? And in principle, we don't know what to do with it, all right? So because look, if I ask you to calculate this quantity, you can do this formula, but still, how do you know what this is? So this is something which has to do with the short modes. We said we don't know how to do the dynamics of the short modes, so how are we going to deal with that dynamics, okay? So there is no way to do it, in fact. We don't know how to deal with short modes. So the only thing that we can do is to average over the short modes, okay? So what it means is that we want to keep somehow the realization of the long modes fixed and ask ourselves, what happens if we have all possible like realizations of short modes and I average over them, okay? So I want to understand what is some, to study the long wavelength dynamics, I want to understand what is some average like trouble that the short modes introduce for the long wavelength modes. For those of you who know something about quantum field theory, this is the procedure which is equivalent to integrating out like heavy fields from the Lagrangian, and you end up with the effective theory, which has only light degrees of freedom, and you don't have to know what are the details of the high energy physics, but you're going to introduce some extra terms in the Lagrangian, in the equation of motion, and all the terms are going to be all possible terms allowed by symmetries of your theory. And so this is why this approach, where you keep some effective terms in the stress tensor, is called the EFT of large-scale structure. So it is like effective theories from the quantum field theory is inspired by this kind of procedure, where you integrate out like very heavy particles. And in this particular case, we are averaging over very small wavelength fluctuations that we don't know how to deal with, but we can just average over them and generate some terms in the equations of motion. So what kind of terms do we generate, okay? So as I said, again, there is a way to be a bit pedantic and calculate these things in more detail, but you can even guess what kind of stress tensor you can possibly get from this procedure, okay? So the stress tensor we can get must be something that depends now only on the long wavelength fields. It will have two parts, a part which is dependent on the long wavelength fields, and the part which is completely independent on the long wavelength fields. Like, for example, maybe this one, okay? Just 1 second. So in fact, you can write down all possible terms allowed by symmetry. And for instance, let me give you an example and explain what it means. Di dj phi, you can have phi long, of course. You can have L2 of t delta ij. This is the Kronecker delta, times, for example, Laplacian phi long. You can have some delta tau ij, which does not depend on the long modes. And you can have infinitely many other terms. I can keep writing down all possible terms, and I will explain what all these possible terms are. But there was a question, yes?
I'm confused. Maybe I don't understand what tau ij tilde L means, because we're saying that the stress tensor should act on the small scale.
Yes. So no. But this is the point that I'm trying to make. There is no clear separation between long and short scales. They talk to each other. In these equations of motion, there are terms where you have multiplication of fields. So if you have two short wavelength fields, they can combine to give a long wavelength fluctuation. So the question is, like, how do we know what kind of long wavelength fluctuations do we get without knowing the details of the short scales, okay? And so this effective stress tensor basically has some form that I just wrote down, which was the following. I wanted to say the following thing. Let me do like expansion in the same way as I did here. So for instance, you see that there is some sense in which these average quantities are some naive answer plus higher derivative corrections or higher order perturbation theory corrections. So here, if I stay at the lowest possible order in perturbation theory, and I write down the fewest possible number of derivatives, then the only thing that I can write down is something like that. There is some unknown coefficient which depends on the short scales, because I averaged over the short scales. And now this unknown coefficient is some number that I don't know. I cannot predict it. But what I know is that there is no long wavelength dependence here. It's just some number which depends on time. Times, what can I do? Well, there is the tensor tau ij. So therefore, I can write down all possible terms allowed by symmetry. I can either do di dj phi. This is an observable. It's a tidal tensor. It's a perfectly valid candidate at leading order in perturbation theory. Or I can do something which is isotropic, like delta ij, and then just put these two derivatives like that, so which is basically just delta long, okay? And then there is a part which is stochastic tau ij, which basically does not depend on the long modes, but it's just some short modes which randomly in some patch of the universe look a bit different than the other patch of the universe. And there is some stochasticity. If you look here, you're going to find one kind of short modes. Here, you're going to find another kind of short modes. And the fact that they vary from one patch of the universe to another randomly because of a random realization of the initial conditions introduces some extra stochastic term in the stress tensor, which is uncorrelated, or it doesn't contain the long wavelength fields in it. So there are two kinds of terms. Those kind of terms where you do have some dependence on the long wavelength modes with unknown coefficients because you averaged over all possible short scales. And then there are some stochastic terms which do not depend on the long modes, but they also come from the fact that you average over short scales, but simply in different patches of the universe, there are different realizations of short modes. So now, you see the equations of motion then become very simple. If you plug this thing here, this derivative, dj, is going to act here, is going to produce delta. Here you already have delta, so both of these terms are going to get identical form. And if you just expand this 1 over 1 plus delta long, and you want to keep the lowest order in perturbation theory, it is as good as just setting it to 1. So it doesn't play any role, because this is going to be delta long times something which already contains delta and will be higher order in perturbation theory. So in general, the logic here is that you should start from these equations of motion and write down for the stress tensor all possible terms allowed by symmetry, which means rotational invariance, translational invariance, equivalence principle, and so on. So for instance, we cannot write down anything which depends only on the gravitational potential, because gravitational potential is not an observable. You have to have at least 2 derivatives on the gravitational potential to make it a tidal field, or delta to make it observable. Okay? So this is why this is the only thing that we can write down. And if you go to higher orders, for instance, I can put more derivatives. I can put, for example, I can do di dj phi all squared. I can do Laplacian of di dj phi. Sorry, this is not squared. This is not going to be good. But for example, dk and then dk dj phi, things like that. So all these tensors are allowed, and they all have unknown coefficients. But you see, the thing is that as I add more fields or I add more derivatives, on large scales, these terms are less and less important compared to these terms. For the same reason as this term here was much less important than this one if I focus on large scales. So we cannot, in other words, for the dark matter system, we cannot like solve short scale physics. We can never understand how to do that. But what we can do is to average over all possible short scales and find out what kind of terms this produces as a source for the long wavelength fluctuations. And these terms can be organized in some perturbative expansion. So there are 2 expansion parameters. There's expansion in di dj phi, which is roughly speaking expansion in delta. So you have a perturbation theory expansion. For instance, this term is of order delta square. This is only delta. So if you're on looking at the large scales where delta is small, this is much small. For example, this one is smaller than this one. And then there is another expansion, which is expansion in derivatives. This expansion in derivatives, for instance, like this term here has extra derivatives compared to this one, and therefore it is smaller than this one. Yes?
Why don't you have derivatives on the velocity?
Oh, yeah, absolutely. Eventually, I completely agree. So eventually, you have to add also derivatives on the velocity on all possible observable quantities. At linear order, velocity and delta are the same thing. So this is why, for example, you remember from the course of the linear perturbation theory that if you neglect this nonlinear term, then velocity is related to delta. So at linear order, they're basically the same thing. And so this is why I didn't write it down here. But you're absolutely right. Eventually, at higher orders in perturbation theory, there is a difference between velocity and delta, and you have to take also all that into account. But the point is that all these extra complications that are there, absolutely, they are all suppressed compared to this leading piece. And as I'm going to show tomorrow, this leading piece is just enough to make sense of the one loop calculation that we're going to be after. Okay? So this is the conclusion. This is very important. I mean, there is one thing to learn from these lessons. I mean, you can do all the calculation yourself. It's a bit tedious. But one thing to remember is that there is no sense in which you can use ideal fluid equations of motion for the long wavelength fluctuations without adding these extra pieces. The origin of these extra pieces is that they come from small scales that are not under control, and we don't know how to calculate anything. But what we do know is that when we go to sufficiently large scales, much larger than these 10 megaparsecs, for instance, then there is some systematic expansion of possible effects of these short scales. And if you average over them, the only way that they can influence the long wavelength fluctuations is through the well-defined like templates. It can be either this or this. There is some stochastic term or higher order terms, but with some unknown coefficients. But now we have a set of equations which is consistent, which we can close consistently and truncate the hierarchy and so on. So everything is written now in terms of the long wavelength fields, but the price that we have to pay is there are a few unknown coefficients, which are time-dependent, that we don't know anything about. And they come from the details of the small scales. If you change, for example, the nature of dark matter, these numbers will change, because on small scales, dark matter will do something funny, and it will change how it affects long modes. So is this clear? This is a very important point. All right, so let me start, and then we're going to continue tomorrow, saying a few words about. So now we have a set of equations which we can trust. So this set of equations basically is this thing plus a Poisson equation, and tau ij in particular is going to have this form, and we are going to neglect all higher order perturbation theory, higher derivative terms. And the question now is like just doing some algebra. How do we solve these equations? Okay. And that is something that you have already seen last week, at least a part of it. So let me just repeat this exercise. Let me explain how the solution go, neglecting for the moment tau ij. I'm going to come back to that and include it later, tomorrow. But now let's just remind ourselves what happens when we try to solve these equations. Okay, so first of all, the velocity that you have probably seen already last week, that the velocity can be always decomposed into a part which has like a curl and only divergence, okay? So I can write down v like plus v curl into two components, such that the divergence of v curl is equal to 0, and is equal to 0. And this then allows me to define the velocity another velocity variable, which is theta, which is defined as the divergence of v. So you see, the divergence of v is going to pick up only this contribution, and it will not pick up this contribution. And there is another variable, usually called omega, which is given by this, which again picks up this other contribution. Now, I think that probably you know that if you plug, if you now rewrite, for example, the equations of motion in terms of these new variables, what you're going to find is that this variable doesn't have a source in the equation of motion. So the equation of motion for this variable is going to be just given by that equals 0. For example, at linear level. Okay, so this is a linear equation. How do you see this? Well, you have to take this derivative operator on the Euler equation. So if you go here and apply this differential operator, you're going to get omega plus h omega. Also here, you're going to get some omegas nonlinearly. But you see, on the other side, if you keep only these leading order terms, you can make sure, you can check that actually there is no source. And so vorticity, this is called vorticity, is not generated at lowest order in perturbation theory. And it is not there in the initial conditions, but by the fact that we have inflation. So there is no initial velocity, there is no initial vorticity, okay, in the initial conditions. So we are really like safe. We can, at this lowest order perturbation theories we care about, we can neglect vorticity. And all that we care about in terms of velocity is this theta, okay? So now theta, on the other hand, does have a source. So this divergence does have a source, because if you apply this divergence to this equation of motion, then divergence acts here, here, here. But when it acts here, it gives you Laplacian of phi. And Laplacian of phi is delta. And that makes sense, because you see if divergence, if there is some divergence, so for example, there is some flow towards some point, this means that there is some overdensity here. So this is the meaning of this part of the equations of motion. Okay? So basically, the growth of structure at leading order perturbation theory is producing only divergence kind of part of the velocity. It doesn't produce curl part where there is some vorticity. Okay? Very good. So that means that we can make our life simpler by looking at this scalar quantity rather than looking at the whole vector for the velocity, because this component is not important, and we're just going to focus on this theta. So our variables now are going to be delta and theta. And now what we want to do is very simple. We want to take these equations of motion and write them down in terms of delta and theta variables. Okay? Now, the reason why this is a bit complicated is because theta is defined this way. And it's a bit hard to understand how to deal with this differential operator in these kind of terms. Okay? So the most convenient thing to do, as usual, when we have, so these are some partial differential equations. They have time derivatives and space derivatives. And the best strategy to solve these equations usually is to go to Fourier space. Okay? So we are going to introduce Fourier parts. So for example, delta k is going to be integral d3x e to the minus I kx, sometimes delta of x. And the same for theta. Theta of k is going to be d3x e to the minus I kx theta of x. Now, the advantage of introducing these variables is that dealing with differential operators in space is much easier in Fourier space. So for instance, velocity. So look, we have a gradient or divergence of the velocity. So this means that if I go to Fourier space, divergence becomes this. And then what I can do is to write, for instance, that velocity in Fourier space is equal to minus ik over k squared theta of k. Is this clear? So this is obviously an identity. I mean, if I just multiply both sides by ik, I'm going to get theta k. Okay? So the strategy then is very simple. Take these equations of motion, write them in Fourier space, which is easy. It will be Fourier space for velocity field. But now you have a simple formula which will tell you how to replace this velocity field with theta. Okay? And I leave you as an exercise to do it. It's nothing complicated. You just have to do a Fourier transform of some of these products. I mean, it's a very easy exercise. Let me just write down the final answer, which is not here, but it is here. Okay. So the final answer is that now, in terms of Fourier components, delta prime, because of course this always depends on time, delta prime of k plus theta of k is equal to minus, and now here there's going to be some complicated integral, d3k1 over 2 pi cube, d3k2 over 2 pi cube. There is a 2 pi cube Dirac delta. K minus K1 minus K2. And then there is some alpha of K1, K2. And theta K1 and delta K2. And similar equation exists for the other equation. So now theta of k prime. I'm just putting one function of time, not to make things too complicated, and too long. But of course, all these quantities depend on time. Plus h theta of k plus 3/2 h squared omega matter delta of k equals, again, the same structure of the integral, some different function of k1 and k2, and theta of k1, theta of k2. So let me just say a few words about where do these equations come from, and we are then going to show some solutions tomorrow and do like some calculations. So for instance, let me write down what this alpha is. So in this notation, alpha, for instance, is k1 dot k1 plus k2 divided by k1 squared. And the other kernel is 1/2 k1 dot k2 times k1 plus k2 squared divided by k1 squared, k2 squared. So do you have a guess why this is true? Can you roughly see where does it come from? So let us look, for instance, at this piece here. Let us look at the continuity equation. So I can always expand this product. I can write it like V long plus delta long times V long. The V long part only has a divergence times V long, so it gives me theta automatically, right, by definition. So therefore, in the continuity equation, I'm going to end up with something which is delta prime plus theta. So delta prime is just this delta prime, and theta is just this first term where there are no nonlinearities whatsoever. Okay? However, there is also a second term in the equations of motion, which has divergence of this product. Okay? And this one is a bit more complicated. So what you have to do is to go to Fourier space. So this is like a product in real space, which becomes some sort of a convolution in Fourier space. Okay? And so when you act with this derivative, it's going to give you a bunch of k's that are exactly this kernel here. And so let us see, why does it have this particular structure? Well, 1 over k1 squared comes from the velocity in this product, because you remember that velocity in Fourier space has this 1 over k squared terms. Okay? So here I have, you see, theta has a vector k1. So this is why there is a k1 as a vector divided by k1 squared. This is precisely this structure here. So this term comes when I'm replacing, doing the Fourier transform and so on and so forth, having Fourier modes, when I'm replacing this velocity with a theta. Okay? And so then why there is like k1 plus k2? Well, as I said, the product of these two fields in real space is just the convolution in Fourier space. And this convolution usually have this structure where you have k1 and then k1 plus k2. And the reason why there is a vector is because there is this gradient acting on the whole product. Okay? So this gradient acting on the product brings down the sum of the momenta, which is k1 plus k2. And the other vector in the game, which is velocity, has this structure, k1 over k1 squared, because this is what we need in order to write in terms of theta. So it's nothing complicated. You just have to sit down and do a few lines of calculation. And you can do it as an exercise, just to see for yourself. There is really nothing difficult here. And the second line is the same thing. Because now we have two velocities. There will be two inverse Laplacians in the denominator. So there is 1 over k1 squared, 1 over k2 squared for these two velocities here. And there will be some extra derivatives. First of all, k1 and k2 come again from the numerators. And this extra derivative comes from the momentum structure of this equation, okay? But in any case, this is what you get, right? So now these equations of motion are not complete, obviously. There are terms which come from these pieces here. There is something extra. But let me, for the time being, just focus on these two parts, because these extra things are simple to deal with, and we're going to deal with them separately. So let me, for the moment, just look at this. I mean, I'm not going to do it now. I'll do it tomorrow. But I just want to say that the really a bit tricky part of the nonlinearities really comes from these couplings, because at this order, if you trust me that this is all that we should keep, and we're going to see that this is true to fix the one-way calculation, then these terms are just linear in delta, and they're easy to understand how they act as a source for this differential equation, because they're linear in fields. Those are nonlinear, and the question is, like, how do we now solve these equations? Now, the idea, of course, is that we cannot solve these equations in full generality, but what we can do is to solve them perturbatively, and this is what we are going to do. So let me just write in the last few minutes. Yeah. Oh, absolutely. But what I said is that I want to keep only terms at lowest order in perturbation theory, and therefore, if I expand everything here, if I have already those terms, and I multiply them by delta long in the expansion, they're going to be higher order, right? Do you see what I mean? For example, I can write this like 1 minus delta long, well, as multiplying something, okay? And so this 1 is just going to give me the lowest order terms, and these extra pieces are going to give me higher orders in perturbation theory. And my claim is that we don't want to deal with those. But I agree with you. In principle, there are nonlinearities.
Don't think they're in the same order of this, that delta and that vector?
No, well, you're saying that they're second order in perturbation theory. Yeah. And why am I keeping second order fields here, and I'm neglecting second order fields there? Excellent. I'm doing that because there are these derivatives here, you see? Like, there is one derivative here, and there is another derivative that I have to act with to turn this into theta. So there will be two derivatives which are not in these terms here. And so we are going to see how this counting works, because I completely agree with you. It's a bit non-trivial because there are two expansions. One is in perturbations. The other one is derivative expansion. And it is not obvious, for example, how many orders you have to keep in one and how many in other. But we are going to see that, indeed, for the lambda CDM-like cosmology, it is sufficient to keep only the leading counter terms and nothing else. Okay? But in principle, if you want to be more precise and go to higher orders and be more careful, you will have to start keeping all possible nonlinearities also in the stress tensor and evaluate the fields at the nonlinear level, and then things are going to become more complicated. Yes. But let me just do the simplest thing. Okay? So let me just say that what will be the structure of the answer, and how do we get the answer? And then I'll show that tomorrow. So the answer is essentially that, for example, delta, let's call it delta nonlinear of k and t, is going to be something which is organized in like some perturbation theory. So it will be like, I don't know, n goes from 1 to infinity in some sense. And then we're going to have the growth function to the power n. This will be our time dependence. And then we're going to have nth order solution here, which depends on k. Okay. So for instance, if you just look at these equations and say, I want to do only linear theory, okay? Let me just do the linear theory. Then you're going to neglect these nonlinearities, and this is exactly what you did last week. you're going to be left only with this is equal to 0, this is equal to 0. You can combine these two equations and find a single second-order differential equation for delta, which tells you that there are two solutions, the growing and the decaying mode. And you can just find these solutions and see how the fluctuations grow under the influence of gravity, sourced by the Poisson equation, in this linear universe, okay? But now, let's say we want to include these nonlinearities. What do you do then? Then it is also very easy. We cannot solve these equations exactly, but what we can do is to solve them perturbatively, which means plug these ansatz into this solution, which effectively means first solve the linear equations and get the linear solution. Then plug the nonlinear solution here and here. So now this is formally, if you think that there is some small expansion parameter here, which tells you that each order is epsilon times smaller than the previous one, then you have a second order here because you're multiplying two linear solutions. And now this is a source in the differential equation for the second order fields on the left-hand side. Then now you know the linear solutions. You know exactly what is on this side of the equation. You calculate what is the second order solution. It's a bit tedious, but there is nothing complicated about it. Fine, you find a second order solution. Then what do you do next? Well, you take your first and second order, you combine them to give you a third order. Now you have a third order term as a source. Plug it back here, solve the equations, find third order solution. Once you have a third order solution, you go back here and start combining third and first, second to get fourth order fields. You find fourth order solution, and you keep repeating iteratively. And let's see if this doesn't work anymore. Okay. Maybe I should. So this process of recursively solving things in perturbation theory is very well known for differential equations. This is what we always do when we don't know how to solve things exactly. And this is going to lead to some sort of recursive solutions. There were slides here showing these recursion formulas, but I'm going to anyhow come back to that tomorrow and maybe say a few more words about this. So for tomorrow, we want to find the solutions to these equations. Basically, I'm just going to show you the simplest case, like second order solution, and then how through this recursion relation you can generate whatever you want. And then we're going to start calculating something. We want to calculate, for instance, something with these nonlinear fields and see how does it compare to, for example, embodied simulation. Are we getting something which makes sense, or it doesn't make sense, how things look like. But the most important lesson for today, really, and I think this is what I want you to remember, is that the consistent truncation of Boltzmann hierarchy when we discuss Vlasov equation, and the consistent way to write down fluid equations for dark matter on large scales necessarily includes some short scales back reacting and producing long wavelength modes. And this is captured by this effective stress tensor. The logic here is that once we average over the short scales, there are only long wavelength modes left with all possible symmetry allowed terms and with unknown coefficients, which depend on the short scales. And this logic is the same as the one of quantum field theory when we integrate out heavy degrees of freedom. This is why this approach is called effective field theory for large-scale structure. But in reality, it's really just the standard perturbation theory, but with a careful treatment of what happens, how do you consistently truncate Boltzmann hierarchy and take into account short modes. All right, so this is one important lesson. These terms are in principle maybe not very large. We're going to discuss their size. But it turns out that they're very important. They're really not negligible. They have a few % effect at k of 0.1. This is a lot. It may seem like a small thing, maybe, but if you remember that neutrino mass is also a few % effect at k of 0.1, then you understand that not including those is very dangerous, okay? And we'll see more about that tomorrow. Okay, I stop.
So questions for Marko? Yes.
in this last expression you wrote, you have this dn of tau.
Yes.
Does these coefficients, they somehow have some information about the scale in which you are doing this perturbation?
No, sorry. Like maybe I didn't explain very well what this is. So this d is just the growth factor, the linear growth factor for the fluctuations. Do you remember? I mean, look, did you see the growth factor last week?
Yeah.
Right. So look, at linear order, if n is equal to 1, so the first term in this formula is just d of tau times delta 1 of k. Delta 1 of k is the linear field. So this formula just tells you that the nonlinear field starts with a linear field plus other corrections. It just tells you that what is the time dependence of these extra corrections. This is not, by the way, it is not an exact statement. The time dependence is slightly more complicated in general, but to a very good approximation in lambda CDM, we can replace it with this kind of expression. But in principle, this d has nothing to do with the scale where perturbation theory breaks down or anything. It's just the linear growth factor.
But this is explicit in any other way because you already neglected the higher order terms, right?
Yes.
To write the equations,
right.
dynamics.
So,
just because I would expect that this formal series would somehow break if you have some regime for k.
Right. So how perturbation theory breaks down? I think it's a bit more complicated because really the real parameter is what I showed at the very beginning, like the scale where the variance of the density field becomes 1. Okay? So really the variance of the density field, if you want, is one of the parameters which tells you where the things break down. So it's not the growth factor. The growth factor only tells you like how much fluctuations grow. And it is related in the sense that when the fluctuations become very large because of the growth factor, your scale where things break down are going to become bigger as well, but in a non-trivial way. So I think that roughly speaking, this nonlinear scale is like maybe 10, 20 megaparsecs, okay, in real space, or k of 0.2, 0.3, 0.5, I don't know. Like this depends a bit on how you define it in momentum space. Also depends on redshift and so on. But the point is that this is not the end of the story. You should remember that there is also these extra pieces that I'm writing here. So there's a plus counter terms. So there is a contribution from these guys. And then then perturbation theory convergence becomes a non-trivial question. I mean, I think you have to combine both and see simply when it doesn't describe your data anymore. But we understand that this must be the nonlinear scale, which is roughly 0.3, let's say, or 0.5 or something like that.
Can you repeat the argument for neglecting the vorticity?
For the absence of vorticity?
Yeah.
So how do we find the equations of motion for vorticity, first of all? So we see that vorticity is defined as this differential operator acting on velocity field. So if I go to that equation over there, I'm going to be acting with this differential operator on all these terms. Now, all of them are going to give me some vorticity. But you see, when I act on this vector here with this differential operator, it gives 0 by construction, okay? It gives 0 because you can write this. So the other way to write this down is to say that this is epsilon ijk dj dk, okay? Or whatever is the, sorry, let me say this. So this operator is equal to that, where you have to replace another vector on the right-hand side, right? Do you understand what I mean?
Yeah.
So if I plug, for instance, di phi,
it's symmetric.
It's symmetric, and I'm in trouble. And this happens for all those terms that I wrote down. So for some higher order terms, maybe it's not true, but for these terms, it's correct, yes.
Yeah, but why? Because the equation is linear, then the vorticity will be neglected. That I think this.
Oh, sorry. Sorry, I thought maybe you also saw this last week, maybe you did not. But the solution for this equation of motion is that vorticity must go like 1 over a. So if there is any vorticity at any point, it can only decay. Because there is nothing to source it because of these arguments. So there is no source term. There is nothing to produce vorticity. And then the question is, so even if you have some vorticity, it will decay. Now, the extra point is that there is no vorticity in the initial conditions. So in the initial conditions, all velocities are basically 0. And all velocities are generated by just simply doing gravitational collapse towards more massive, like peaks of the density field. And so given that there is no vorticity in the initial conditions, and that even if you have any vorticity, it just decays, never grows, this means that we can just neglect it as these leading orders in perturbation theory. This is what I
meant. I'm just curious about what will happen with the unknown terms on the stress tensor L1, L2, because I think they will appear on the power spectrum, but we don't have any equations for them, like how you deal with them.
Sorry, I didn't quite understand what is the question.
When you write the tau ij, the stress, you have those unknown terms, L1, L2. Yes. So they will appear in the power spectrum when you include these, right? What will you do with them?
Okay, let me give another interpretation of this thing. So this is the same. I mean, another way to think about this stress tensor is that this is in a sense, a bias tracer. Like basically, the situation is similar to the biasing. For example, when you have galaxies and they form in some complicated way, the density distribution of galaxies is not going to be the same as dark matter. So delta galaxy is not equal to delta matter. There is some unknown proportionality coefficient which depends on time. Okay. So what do you do with the bias in the power spectrum?
Marginalize.
Sorry?
You marginalize it with it.
Exactly. So we are going to do the same. Here, we're going to have some free coefficients. We're going to measure them from the data or marginalize. This is exactly the same. So, but you see, including these things, it may seem like, oh, you lose a bit because now you have extra free terms. But actually, you're going to gain a lot in like how reliable and precise your theory is. So the gain is much bigger than what you lose by putting, because we are not putting these terms because we want to, or we don't, they're really there. And I'm going to show some examples where you can clearly see, I mean, it's not possible to deal with perturbation theory without them. But the treatment will be the same as for bias parameters. These are some nuisance parameters that either you measure from the data or you marginalize over.
More questions for Marko? So there will be a discussion session later on, so you can keep your questions for later also. So let's thank Marko for this very nice lecture.